The Navier Stokes equation is the starting point for analyses of many problems in fluid flow. There are two equations. One will be based on conservation of mass, and one will be based on conservation of momentum. So let's do conservation of mass first. So we start off by saying that cap theta, our generic conservation term, is equal to mass. And the term we'll call C is the generic conservation term per unit volume. So that's mass per unit volume, which is the density. And the generic equation for conservation is going to be written like this. So this is the divergence of the flux, where that term, gamma, is the flux. This is the rate of change of storage, and this is a source term. So for conservation of mass, we're going to just let the source term equal 0. So that means there's no mass of fluid that's generated within the control volume. The change in storage term is just simply by substitution the rate of change of the density. And the flux we have, in a generic sense, it'll include an advective and a dispersive term. For this application, though, we'll only have the advective term, which is C times the velocity vector, and that would be rho times the velocity. So we end up with the mass conservation equation looking like this. Now for momentum conservation, the basic conservation variable is mass times velocity. And just to clarify, this is the velocity vector. So that's going to be the component of the velocity in the x1 direction that I'll call u, the component in the x2 direction, v, and w, where we have a coordinate system like this. This would be x1, x2, x3. And so velocity in x1 direction would be u and v and w. Okay, so here's momentum. And the term C is going to be the density of our term to be conserved, momentum density. And so that's mass velocity. And that'll be density times the velocity. So the storage change term is straightforward. We just take the time derivative of the variable C. We'll consider both an advective and a diffusive flux. In general, the advective flux will be C times the velocity. And so by substitution, we get this as the advective flux. the diffusive flux will be the negative of the stresses in the fluid. We can see how this works by taking a look at the shear stress in the fluid. This is the shear stress, and it's equal to the kinematic viscosity times the gradient of the momentum in the x direction with respect to y. This would be for an idealized flow where we only have velocity in x direction. So by substitution, we have a term that looks like that. That's for this idealized flow where we only have velocity in x direction, and we'll have a more general term for the stresses that we'll see in just a minute. Okay, so the flux term looks like this, and the divergence. The source term for this application we'll assume is equal to the body forces in the fluid. So there are the body forces, and we have a vector here that describes those body forces. Many applications, and the ones we'll consider here, will just have a body force in the x3 direction, and we'll say that that's equal to the unit weight of the negative of the unit weight of the fluid. And it's negative because the body force acts down and we have x3 pointing up. So the generic conservation equation looks like this, and by substitution we get this for just a generic for the conservation of momentum. Now we want to simplify this equation to make it a little simpler to work with. So the first thing we'll do is use the product rule on this term. So expanding this term using the product rule, we pull the velocity out and have this divergence operator apply like this. And then we pull the other velocity out and have the divergence operator apply like this. It ends up being, this is the same thing. These terms are the same. And that's because we're first pulling out this velocity and then that velocity in the product rule. And then we also need to apply the divergence operator to the stress, so we get that term there. Okay, so this is one step in really expanding out the term. We'll also apply the product rule here, and that gives this. Okay, now what we want to do is group this term and this term together. They both have a velocity out front that we can factor out. So we'll factor that out and group those two terms together, and we get this. Okay, so this is the combination of these two terms with the velocity factored out. Now, what I want to do is go back to previous page. We'll skip back 2 pages and take a look at this term right here. This is what we got for conservation of mass. And this is the divergence of the density times the velocity plus the rate of change of the density. And that equals 0 if there are no fluid sources. So we come forward here, and this is the same term, the same expression as the conservation of mass. And if there are no sources, then this equals 0. Okay, so up to now, we've just been working with the conservation of momentum. We brought in the conservation of mass to simplify it. And now we're going to introduce the constitutive law for a viscous fluid. It says that the stress in the fluid is equal to the pressure plus a term that includes the strain rates. So this is the velocity. It's written like this. So this is the stresses in the fluid written using the Einstein notation, where the normal stresses are written like this with I and J equal. We would have normal stresses like so. And the shear stresses are written where I does not equal J, like this, and so on. And we'll write this constitutive law in a different notation. We'll say that the stresses are equal to minus, well, we'll just simplify this down and we'll write it like this. And this is equivalent to this, but it's just a little different form, and we're doing this because this is the form that we'll recognize later on. Okay, so what we'll do is to use this and substitute it in for the stress term right there in the momentum balance. And then expanding out. Okay, so this is the momentum balance form of, so this is the momentum equation in the Navier Stokes equation. We saw the mass balance. This is the momentum balance with the constitutive law for a viscous fluid. So let's go ahead and write this out on the next page. So here's the equation that we had on the previous page. Now, in many applications, we'll say the fluid is incompressible. If we use water, for example, that's often the case, at least for many applications. And if that's true, then the density here in this term comes out, and we can write it like this. Now, this equation contains 5 terms, and it's useful to take a look at them and just try to visualize what they'll indicate. So the first term here, this is the change in the velocity with time. And so this is accounting for unsteady processes where the flow is got a transient nature to it. So this is the unsteady term. This term here is got the divergence of the velocity in it. That's the divergence of the velocity. And it's the divergence of the velocity multiplied by the velocity. And this is called convective acceleration. And it accounts for flows that have converging flow lines. And I need to rewrite that. That should be del P, the pressure gradient. And this term here, this is viscosity, recall. And this stuff in here is the strain rate. This is the viscous dissipation term. And this is body forces. Now recall, this has all been from the conservation of momentum. We also have, we started with, the conservation of mass. That's what we came up with. This is incompressible. Then the density is not going to change with space, so it comes out. And it's also not going to change with time, so the time derivative is 0. So if it's incompressible fluid, and we can divide through by the density. And so what this says is that to conserve mass for an incompressible fluid, that the divergence of the velocity has to equal 0. Okay, so we've got these two conservation equations, the one that we show here and here for incompressible fluids. I've written these in this particular way because this is quite similar to the way that these equations are written in Comsol. So if we open up Comsol and add a laminar flow physics node, and if we select this equation tab, we see the equation that's being solved for this laminar flow physics. This term here we recognize as the unsteady convection term. This is the convective acceleration term. We have del dot into P, that's the pressure gradient. And we've got del dotted into this term here, which is the viscous dissipation term. And here's the body force. And so we recognize this conservation of momentum. And here's the divergence of the velocity times the density. So we recognize that as mass conservation for this flow problem.